and I'll be talking with my partner here today on managing large FLASK applications on Google App Engine. So I'm currently the CTO at FunPlus. I'm really so excited to be here today. This is my first time at PyCon, and it's nice to see a lot of people here. All right, so Yemisi.
Okay, hi everyone. I'm Yemisi Obielodan. I'm currently the product manager at FunPlus. I also have experience building softwares, and well, I write code as well. So today, like Emmanuel said, we'll be talking on managing large FLASK applications on Google App Engine. So I'll just start. All right. So first, I'll start with where we work. So we work at FunPlus, and FunPlus is a cloud-based data collection software. So we help businesses collect data both online and offline. We also help them analyze this data collected. It's also a fun place to work, really. So I have... Sorry.
So we actually had a video here.
Okay, I was trying to play this video, but...
To show our colleagues goofing around after work, but...
Okay.
I guess
apparently it's not playing. I just wanted to show a quick video of after work time.
Great.
Oh, it is.
So those are some of my colleagues.
I can see it. Okay, I'll just move on. So, okay, this talk will be based on our experience with our product. So our stack at FunPlus is based on Python 2.7, FLASK, Google App Engine, Cloud Data Store, Cloud Tax like TaxQ, then AngularJS 1.5. Yeah, I know AngularJS is old, but that's what we run on now. So then this is just a quick overview of what the talk will be on. So for the next minutes, like 30, 25 minutes, we'll be covering FLASK. So just quick definitions of what large applications are, FLASK and Google App Engine. We'll be talking on FLASK as well. FLASK, so the FLASK application structure, blueprint, and request routing. We'll be talking on App Engine as well. So App Engine, Cloud Data Store, and the Google Cloud Platform in general. We'll be talking on scaling, so performance, effective GCP utilization, and problems we've encountered using App Engine. Then, of course, there'll be time for questions. So I'll just run through just a quick definitions of what we'll be talking on. So what is a large application? So we're just trying not to assume knowledge here. So a large application, for the sake of this talk, is an application with a large number of users, high requests per second, distributed servers, and a large data volume. So FLASK framework. So a lot of people here will know FLASK, but I'll go over it again. So FLASK is a micro-web framework written in Python. So I get a lot of questions where people ask me, like, how would you use FLASK in production? I mean, I still got the question this morning, why FLASK? And I said, why not? I mean, I know there's Django, but why not FLASK? So yeah, we do use FLASK in production, and a lot of applications, like large-scale applications, are built on FLASK. It doesn't really matter that you don't have everything coupled by default. So yeah, with FLASK, you get just a micro version of things. Then it supports extensions, so you can add extensions to just get what you need or the functionality you need. FLASK is compatible with Google App Engine. So if you want to run on App Engine standard environment, FLASK is just works by default with it. So what is Google App Engine? I don't know if does anyone here know about Google App Engine? Google App Engine, sorry. Okay, all right, great. So Google App Engine by Google is a web framework and cloud computing platform. So just like Heroku, right? So it is used for developing and hosting web applications on the Google Cloud Platform. So you have like servers and data centers, all like hosted somewhere in the cloud. I mean, cloud is somewhere, but cloud. So they host the applications for you, and it's like there. So the applications are sandboxed, and they are run across multiple servers. So later on we'll talk about like some of the benefits of Google App Engine, but I don't want to waste too much time here. All right.
Okay, all right, so one of the questions we encounter a lot is, why Flask, like why should you use Flask, and like she has said, why not? So I'm going to go over the application structure we use, and that has worked for us. So one of the major differences we have between, say, Flask and Django is that it doesn't impose a particular structure. So you are free to be creative with your layout or with your arrangement. It's all up to you. So, as usual, we have heard about microservices and large Flask applications, or rather, large applications in general should be broken down into microservices. I mean, in the very least, you should have a front-end service and a back-end service. So the use of this is, the interaction with the user is fluid, and then it remains responsive. Say, for instance, on our platform, Form Plus, when users come online, they want to create forms, they want to edit forms. That action should be instantaneous. But then we have some other long-running tasks, or you can say actions, that happen in the background. Say, for instance, the user wants to copy responses from our data store to their, say, Google Sheets. Now, that's not something that happens instantaneously. I mean, a number of things could go wrong. Sheets could be down, or there could just be licensing issues. You don't want the user to keep waiting. So you kick off a task to run in the background, and you tell the user, okay, your data is being exported, or something to that effect. And then you run this data-intensive task in the background, and then the user experience for the entire site doesn't just go into a halt because somebody is exporting, say, responses of about, say, 1 million users. So, like I've said, this ensures the application is responsive, and also there's nothing micro about microservices. I mean, we have microservices that are monoliths in their own right. So it's just a term, to kind of break down a larger application into smaller, more manageable bits. Okay, so I have here a sample outline. Okay, so for instance, you have an app with an admin section. Of course, the tasks run the long-running actions of the user, say export to Sheets and copy to Google Drive. Then we have a blog, say integrated with the app, and then we have the site. So one thing that Flask gives, we might be familiar with that, is the concept of blueprints. So a blueprint is like a micro app in itself. So I mentioned earlier that even though you have microservices, a microservice in its own right could be a monolith. But then you could have functionality in that same microservice that could be refactored into blueprints. Say, for instance, I'm going to be using our platform a lot because, hey, I'm familiar with that. You have something that sends emails to users. You have another service that, say, gets input from users. And these two actions are mutually exclusive, but they reside in the same microservice. So you could create a blueprint for handling, say, communications with Sheets, create another blueprint for handling user input from forms or from mobile, and then what you have is, in future, let's say you want to refactor that existing microservice into, that existing microservice along the blueprint into other smaller microservices. It makes it easier because you just lift the blueprint out, and then you can make it a Flask app in its own right. So those are some of the advantages. Of course, we run on Google App Engine, and the mechanism by which Google App Engine achieves this is called services. So previously it was called modules, but now, I mean, everybody's getting to the microservice bandwagon, so they call it services. So in Google App Engine, you could have multiple services in your project where you deploy each individual directory to a separate service. And then there's something called a dispatcher. So you configure your rules in your, say, dispatch in the YAML, and then you can say, okay, all responses to /blog should go to the blog microservice, or requests to /task should go to the tasks microservice, and so on and so forth. Also, one thing I'm going to touch on here, it's, okay, registering blueprints, which is on the screen. So you can register as many blueprints as needed for your apps, which is why I mentioned earlier that you could break a microservice into various blueprints along lines of similar functionality. So it's a kind of grouping to aid in your code organization. There's really nothing, so Flask doesn't really enforce a structure, but in line with good coding practices, you should impose a structure on yourself and on your team so that it's easier when you are developing going forward. One thing some people would notice is that all our microservices in the previous slide were in the same directory. And I know people who say, oh no, for you to do microservices, each microservice must be in its own repo. Well, I would say it depends, really. There's no right and wrong answer. Say they're a large team, for instance, you are at Google, where an entire department is responsible for maintaining just one microservice. Of course, it would make sense for you to put the code for that microservice in a separate repository, because you have an entirely separate team. Just like saying you want to host YouTube and say Gmail in the same repository. I mean, they are basically two different entities with different communication structure and different heads. So it really will make sense. But say for a smaller team, like we have at FunPlus, it's actually more of an overhead to separate these into separate different repos. So also there's Conway's law, which says that the design of software mirrors the organization in which it's built. So we're a small team, so we tend to have everything in one repo, and then we can have a centralized place to have reviews and so on. So one more thing I'd like to talk on is request routing. So most times when you look online, you see tutorials, and then you see quick one-page applications on how to, maybe introductions to FLASK. You usually see the method, the function way of defining your routes. So that means you create a function, and then you decorate it, and then that's your route. But when you are building large applications, you want to have a lot more control. You need to be able to, say, inherit functionality across different classes. So FLASK offers you a class called method view that you could use to create more robust views. And then, so you could have, say, all applications that require authentication could inherit from a base authentication route. And then, by default, they have all the logic you've factored in. And you could also use decorators with that pattern too. So, I think I'll hand over to Yemisi.
All right. Okay, so I'll just continue with App Engine. Emmanuel has talked a bit on FLASK. So, usually you wouldn't use App Engine alone. So, App Engine is under Google Cloud Platform, and Google Cloud Platform comes with a lot of things. So, I have a diagram here, but I will just quickly walk through what is on the diagram. So, we have the Cloud CDN, App Engine, Cloud Storage. I will talk about some of these things in the next few slides. So for serving dynamic content, we have Memcache, Task Queue, then Cloud Data Store. And for log processing, we have Cloud PubSub, Cloud Data Flow, Cloud Storage, BigQuery, and Stackdriver. So of course, I won't be explaining everything, but I'll just touch on a few ones in the next slide. So, okay, so I'll start with Cloud Storage. So Google's Cloud Storage is a file service. So basically, it helps you host your files. It is intended for developers and system admins. So cloud storage comes with a lot of benefits. One, it's actually very cheap. Like, cloud storage is very cheap compared to like other places you get that. I think you get gigs for a very, very small price. Okay, so usually, like for us, what we use cloud storage for is we store files. So some of our users use, they upload files to our servers, and we store them all on cloud storage, which is like very cheap for us as a startup. So some of the things cloud storage like allows is, it allows you to store and retrieve objects, which they are not necessarily files. I mean, some people, you can even host a website. You can like host a website from cloud storage. You can serve a website from there. So it features global edge caching, versioning, OAuth, and other things. All right. So we have Cloud CDN. So as every CDN, Google has their own, and they call it Cloud CDN. So it uses Google servers worldwide. And the good thing is the servers are like at different locations, and you can even choose like where you want. So it provides faster delivery of content to your users, and we use CDN as well. And I think cloud storage files are served from there as well. So if you are using App Engine and you have your assets, so you have an assets folder that has like your CSS, your JavaScript, and just your assets files basically. So it is hosted on Cloud CDN, then it pushes it when you like deploy. So we have cloud tags, which are known as cloud task queues as well. So if you're familiar with App Engine, task queues, but they officially call it cloud tags now. So what Cloud Tax does, or tax queue does basically is, it helps you like applications. So when you send a request, you can queue all the requests on like the tax queue. Then whenever a tax needs to be executed, it is called. Do you get? So if you have like, let's say you have 10 tasks to run, you basically send them to the tax queue, then they are queued there, then it allows each task to run. And on Cloud Tax, we have the push queues and the pull queues. So push queues run tasks by delivering HTTP requests to App Engine Worker Service. So I'll just quickly give an overview to that. So if you are running push queues, you just send all your requests, then it's there. Then whenever it's time for it to run, it just goes. However, for pull queue, you can kind of state when it would run. So for pull queues, it rely on other. So when it is time for pull queues, when it is time for it to run, then it starts. So you rely on other worker services to fetch tasks from the queue on their own. I'll go to Cloud Pub Sub. So Cloud Pub Sub is publisher subscriber. Pub Sub publisher subscriber. So it's a real-time messaging. Let's say like a WhatsApp, not like messaging platform in the real sense of it, but it's a real-time messaging service. So like a WhatsApp group that allows you to send and receive messages. Not messages as like chats, but messages between services, basically, between independent applications. So when you're using PubSub, you can broadcast messages from publishers to like subscribers via channels. So like individual WhatsApp group are channels. So many subscribers. So subscribers are just like, oh, if let's say we have a notification tax and a file upload tax and maybe another tax, right? So you can just say, okay, everything regarding file uploads should go to file uploads, and it's published on that channel. That's the channel for it. And everything on as regards notifications should be on that channel, and it is published there. So the benefits or main benefits of Cloud Pub Sub is that it allows the decoupling of background and long data. So all your requests don't have to be in one place. You basically like just push it to different channels where they have to be. So then there's the cloud data flow as well. So especially if you, okay, I'll get to BigQuery, but data flow is a fully managed service. So what data flow does really is, it allows you to integrate with other services. So when you have a large amount of data set and you want to kind of stream it somewhere else, it helps it, especially with BigQuery. So you use data flow to just get the data from one place to another. So it helps with enriching data in stream. It also integrates with Google other services in Google Cloud Platform. So Google BigQuery. So BigQuery is like a large data set, like a large data warehouse, sorry. It is highly scalable. So if you have a huge amount of data, so for us, what we use BigQuery for is, we use data store as our database, that's cloud data store as our database. Then for BigQuery, we push like the large amount of data to BigQuery for analysis. So for example, most people use BigQuery for online analytical processing. And so if you want to generate reports, time series, you want to get metrics of your users, metrics from the data you have, you can push the data to BigQuery. You can write queries there, and you can also integrate with like other BI tools like Metabase or Google Data Studio, which is still in beta. So Cloud Data Store. So Data Store is like the database for Google App Engine. It is, of course, you can use, you don't have to use Data Store, but it's just like, it integrates fully well if you'll be using App Engine. So it is a NoSQL database. There's a quick sample here that App Engine is to MongoDB as what, Data Store is to App Engine as what MongoDB is to MinStack, and App Engine is to MySQL, and to App Engine as MySQL is to LambStack. So Cloud Data Store is a NoSQL database, and the good thing about Data Store is that it automatically handles shredding, replication. It provides you with like available and database. And I think the advantage of Cloud Data Store for us is that it scales automatically. So you really don't have to bother about that. So it just takes care of that for you. And yeah, we have a very short comparison of what Data Store, MongoDB, and MySQL. So if you're very familiar with MySQL, we have tables, we have rows, and we have columns in primary key. So what is called table in MySQL and what is called collection in MongoDB is known as kind in data store. And what is called rows in MySQL and document in MongoDB is known as entity in data store. So for individual object data, so like for each entity, we have properties in data store, while for each document in MongoDB, there's a field, and for each row in MySQL, there's a column. And of course, the unique ID is called primary key in MySQL, key in MongoDB, and as well key in data store. So here are some merits of using App Engine. I think the most popular reason why people use App Engine, what everybody knows App Engine has, is that it handles most of the work for you. So with App Engine, you really don't have to bother about a lot of things. App Engine like, just takes care of your operations. Like, we are a very lean team, so it helps us like infrastructure, scaling. Of course, you still have to do some work, which we'll get to like later, but it takes care of so many things for you. So your software updates, your security patches, infrastructure, scaling, automatically you just like deploy your app, and all those things are already in place for you. And that thing is that once you deploy it to App Engine, your instances are like distributed to any server, so you don't really have to bother about that. Oh, where am I deploying to? Or you want to set up where are your servers or something. It just takes care of it. Everything is in the cloud, so you don't have to bother about it. Of course, there is automatic load balancing, scaling, and fault tolerance as well. So I think the major benefits of App Engine is that it takes care of a lot for you. You really don't have to bother about doing a lot of things on your own. So okay, I think I've talked about this earlier. So.
Thank you. Okay, so we are back on scaling. We mentioned earlier that we were looking at building large applications on Google App Engine with FLASK. One of the major issues of large applications is that you want to scale. You have a lot of users, you have a lot of requests, and you're up at night wondering what could go wrong. So we are going to see some of the issues we had, and what we try to do to mitigate those problems. Okay, so a great man once said, he who thinks the soup is too much for the eba cannot handle scale. I think that great man is Pete Edochie. I mean, you can tell him I said that. So, one of the first problems we encountered was out-of-memory errors. I mean, when you are a small application, if you have out-of-memory errors on Google App Engine, what you do is you go in, you increase the instance memory, and then you continue life. But as you begin to grow, you get to a point whereby you've reached the limit. I mean, there's no more memory to give. What do you do? So, in case in point, I think Yemisi would like to take the background.
All right. Yeah, out-of-memory errors. Anyone that uses App Engine will not be strange to this error. So this is just like live examples of like live problems we had. Though we just mentioned like 3 of them, and we've come to it. So for out-of-memory errors, one good thing is, or one example here is that for our application, we have an application and we integrate with a lot of other services like Google Sheets. So when people so we have an application, people submit a form, and once they submit, the request goes to their Google Sheet. So like whatever is submitted, lives update into their Google Sheet. And there's a communication between it. And there are a lot of like tags. We talk to Sheets, and Sheets talk back to us. Okay, what's the current data here? What are you updating? And all that. So when we start that, there are a lot of tags in place before the submission is finally updated into Google Sheets. But because of memory errors, which Emmanuel has touched on, we then have problems where before the task is even completed, that is just the final task of updating one response into Google Sheets, we get out of memory errors. Basically, like we ran out of memory on just updating one task. This was a huge amount of problem. In fact, we've not fully solved it. We've just found one of the cause, which is Sheets, and
all right. So earlier when we were listing the things you get when you're on the Google Cloud platform, in addition to App Engine, we mentioned Stackdriver. So Stackdriver is a pretty awesome tool. It allows you to see your logs, your errors, and we're able to do some, troubleshooting, and found a particular library that on Python 2 uses about 30 MB additionally per request to Sheet. So what we tried to do was to refactor that particular logic out of our app into cloud functions. Now, if you're familiar with the Google Cloud Platform, you would discover that this is actually in beta. Uh, Google Cloud Functions just started supporting Python 3 last month, like literally last month. So this is like bleeding edge. And we are betting on it because this is giving us a lot of headache. And what we've done is we've refactored the code to actually call a cloud function. So the difference between cloud function and App Engine is when App Engine runs, each subsequent request reuses the same instance. So there's kind of like persistence of state between requests. But for cloud functions, it's similar to like AWS Lambda functions. So when a request runs, and it does its work, and the instance is queued, and then the next request comes in to like a clean, fresh slate. So what this means is that the additional memory that is being used from request to request in App Engine does not happen in cloud functions. So, I mean, we've seen some pretty good results using this, and even though it's in beta, we are ready to risk this. Okay, so another quote. This says, there are two hard things in computer science, cache invalidation and naming things. So we had a problem with cache invalidation, which I think Yemisi will give the introduction.
Okay, so another major problem we had is cache invalidation, and I'll just give a quick sample of how it affected us in real time. So for every user on our platform, they have a monthly subscription. So that monthly subscription gives them an allotted quota to use. At the end of the month, the quota is reset. So let's say if you have access to 1,000 submissions in a month, at the end of the month it is reset like to 0, then we start again, we start the count again. But what happened now was we had some users who didn't have their monthly subscription quota reset. So let's say you receive 700, you have a total amount of 1,000, you receive 700 this month. The next month you receive 300, which makes it 1,000. So usually the 700 should have been reset to 0 after 30 days. We have now had problems where this was not happening. So basically, at the second month, 700 starts, like it's still there, then the count starts again from like 701. By the time you've received like up to 1,000, which is supposed to just be the maximum for 1 month, the user is unable to receive like new submissions. And for us, there's a business logic that once you reach your maximum submissions, you get to, your form is closed and you can't receive any other submission. So this became a problem for a lot of users. We didn't know why this was happening for a long time. Like, this is supposed to reset on a monthly. We kind of investigated a lot of things, and we found out it was happening because of cache invalidation.
All right, so the cause for this issue was every month we run a cron job that runs through every user on our platform and resets their submission quota if they have a valid subscription, which means that they've paid for the next month. So the recommended way of doing this on the Google Cloud Platform is to run what you call migrations. So migrations, you can think of them as like map reduce jobs. So you take all the users and then you run them through this pipeline. And then for each user, you state what you want to do. Check if the subscription is valid and reset the quota. But there's an issue because when you do this, the efficient way of persisting your changes is to batch all your writes at once. So you don't write for each user. When you fetch 100 users, you update them, you write them at once. You don't write them individually. But when you batch, it writes straight to the data store and bypasses memcache. One of the benefits of App Engine, or one of the benefits of the cloud data store, is that you have caching by default. So for instance, let's say you have an application running on the LAMP stack, you're using MySQL. What you usually do is that you get Redis and place it in between your application and the database so that frequently used data is in, is in Redis, and then you don't have to hit your database every time. So memcache also does that on App Engine automatically by default when you use the NDB library. But that convenience can come back and bite you if you don't really take note of it. So how we solved this problem was we skipped the in-process cache for updates and then told it to update both memcache and the data store. But the downside of this is the migrations take longer to complete because you're actually writing each individual entity directly into the data store. But the problem is fixed. The last problem we want to talk about is data store contention. I mean, a very simple way to visualize this is the image of A lot of people trying to get into a bus through the windows, through the doors, any way possible. And as usual, Yemisi will take the background.
Okay. So data stock contention, it is one of the popular problems you may experience when you're using App Engine as well. So this may not happen if you're like maybe testing or creating just test applications on App Engine. But for us, we have like some users with very large forms that they receive like hundreds of thousands of responses. So this means they get updated like every second, not like every millisecond basically. And for every form, there's a submission count. So this means like, oh, you want to know if you have just 10 responses or 50 responses or 100 responses. And the way we update that is once a form is submitted, we update, we have an object where it is updated, the count is updated. And it became a problem because we started having contention errors just because we were trying to update a submission count. This was the problem we experienced, like an example of the data stock contention problem we experienced. And we had to investigate what happened. And Emmanuel just...
All right. So for this problem, I'll talk about one of the frequently discussed solutions before I talk about what we did. So you might have heard of what is called a sharded counter. So that means a counter that is parallelized or duplicated into different areas. So instead of, say, just imagine a lot of people trying to enter this room. Instead of having one door, we have 10 doors. That means more people can gain access instead of everybody trying to cram through just that one door. So a sharded counter is similar, but to implement sharded counters effectively for our problems, we would have to have used an automatic scaling sharded counter, which means that as the number of responses to a form increases, it decreases the amount of counters that are recording submissions for that form. The downside is when the amount of users go down and you're not having that much traffic on the form, it doesn't reduce the amount of counters that's provisioned. So you still have that high number now that the form is basically not receiving any responses. So we couldn't go through that route. So what we did was we had to tweak the task queue model a bit, and then there's a concept on App Engine, rather on task queues, where if you have a task with a name, you cannot reuse that name for at least 7 days. So we used that and generated a name using the form ID and the date of submission. And with that, we're able to constrain the number of times the submission task is run. So basically, when the submission comes in, we don't start immediately. We say, okay, run this task, say 10 minutes in the future. And then let's say 1,000 responses come in after that. And in 10 minutes time, it just batches all 1,000 of them at once and then writes to the data store instead of trying to write 1,000 times in 10 minutes. So, so what we did was to combine this with an entity in data store that tracks the amount of submissions that have been recorded in that period, and then we'll do a batch update. So I think this comes to the end of our presentation, and we'll be taking questions, if any.